introduction. Yeah, you're right, I'm not really going to talk about stamp collecting. It's a great honor for me to give this lecture, particularly in memory of John Fox, who I didn't know, but I did read about him, and I do know that he did work in fluid mechanics, both in biofluid mechanics and in networks in tunnels, and I'm going to say something related to that in the course of this lecture. I'm going to start with a little bit of history about how I got interested in the problem I'm going to talk about. It began, I think, one of the big influences in my life, of course, was my PhD supervisor, Stuart Turner, who sadly died last summer at the age of 92. And he introduced me into issues associated with density variations in flow flows and mixing problems. And he was motivated in the late 50s and early 60s by issues associated with methane layers in mines. The methane is a gas lighter than air. It accumulates at the ceilings and flows along mines, and of course is flammable. When the concentration of methane in air is something between 5 and 15%, it can ignite, it can explode, and it causes lots of injuries, and it was a concern. And in fact, much of the work that was initially started here began with the Safety in Mines Research establishment. I list a paper here, which was based in Sheffield, so it's local to Yorkshire, and it's a problem that I think has been interesting for a long time. And what Stuart did was to take an airflow problem and convert it into a water flow problem, where he had fresh water interacting with salt water, so this is the methane layer, but it's dense compared to less dense. But we know under certain conditions you can reverse these things. And so what you can do is model something that happens in a mine, in a laboratory, and that's an interesting problem. So that was kind of an inspiration for me when I was a PhD student. And I also got interested in this problem, which is still a current problem, which is what happens when you want to flush out a pipeline and replace air with gas. Very practical problem. As I said, gas, methane, and air will ignite under certain concentrations. This is a difficult problem. What's typically done is to take, you have air, you first of all introduce nitrogen, so you have a slug of nitrogen in the system. Up here. Whoops. Oh, there's no point. Sorry. Let's go back. So nitrogen, and then you add gas with a nitrogen mixture to avoid the gas and air mixing directly. Now, again, these up the top of the densities of those three mixtures. Methane is about 0.7 kilograms per meter cubed, up to air at 1.2. And those density differences cause buoyancy effects that stratify the flow. So here's an example of measurements taken in a pipeline with methane. And you can see that the methane sits on top of the air and produces a stable stratification. So this is buoyant compared to this air below. And it's a very important practical problem, and it's now being considered for use of hydrogen. So hydrogen in a system where hydrogen is even less dense than methane. That's about 1/10 the density there. So these problems become even more important. So one of the questions is, how do you avoid mixing, or how much mixing takes place, depending on how hard you push it, and so forth. Very practical questions. Another example that I got involved with to do with this, which is a bit more extreme, is what happens when there are fires. Fires produce hot gases. They are buoyant. I worked closely with the health and safety executive on the King's Crossfire, which occurred in 1987 and killed 31 people. Many of you will remember that tragedy. And that was because hot gases rose up the escalator shaft and didn't mix with the surroundings and actually ignited the wooden escalator all the way up. And it didn't mix because it was confined by the geometry of the escalator shaft. I also got involved in working with the Channel Tunnel. The question there was, if you have a fire in the Channel Tunnel, I know there have been many, of order 6 or 7 in the last few years, how hard do you have to blow to make sure all the combustion products go one way, and that means all the people can escape by going the other way. So these questions, again, are associated with stratification, buoyant fluid over less buoyant fluid, flow in the system, and how much mixing takes place. So these are very important practical engineering problems that are going to motivate what I talk about. Another problem, which I think is also relevant to this, and on a much different scale, concerns the climate issue. We all know that the oceans are heated at the surface at low latitudes and cooled at high latitudes. And so what happens schematically shown here, cool water is produced at the poles and sinks to the bottom of the ocean and flows equatorward. The heat that's put in at the surface is buoyant, produces buoyant fluid at the top. And this has to mix down to avoid this whole ocean basin filling up with cold water. So how does that happen? What's the rate at which that happens? What does it depend on? And can you predict it? And this is a very tough problem for a climate scientist. They take the globe and divide it up into very large grids, tens of kilometers in size. And inside one of these grids, all these interesting processes take place. And what you're trying to do is to work out how the heat that's placed in here gets mixed around with all of these various physical processes taking place. So, for example, you have currents, waves, interactions with the bottom topography, producing flow in the ocean, and you want to be able to predict the global rates at which the heat is taken up from the atmosphere. And to give you a specific example, we look at the equator. There is a flow associated with equatorial flows flowing towards the east, above and towards the west, a shear flow in opposite directions, again with buoyant fluid above, less buoyant fluid. And the question again here is, can you predict the rate at which this mixes? How does it do that? If you just know the large-scale fields. And the reason that that's a challenge is because what really happens on very tiny scales. So really to change the density of the fluid, you have to do things at the molecular scale where the diffusion matters. And that occurs at very small scales, in the ocean of the order of a millimetre or a centimetre. And we're looking at this over hundreds of kilometres. So how do you deal with that range of scales? So what I want to do in this talk is to address these questions. I want to ask, what form does mixing take place in a flow which has a stratification and has velocity differences, a shear flow? Can we predict the rates at which these things happen given the mean flows? How do these depend on the fluid properties? Does it matter whether in the ocean, for example, there's temperature we're concerned with or salt, or in a gas, methane or hydrogen? And what are the energetic pathways? How does it actually happen? Okay, so this is of course not the work I've just done by myself. This particular topic I'm going to talk about started about 10 years ago when I had an undergraduate student called Colin Meyer who spent a year in Cambridge and came to me and said, I'd like to write an essay. And I said, which we asked people to do in their fourth year. And I said, well, would you work in the lab to write your essay? And he said, yes, I'd love to do that. And so he worked on, we developed SID, the Stratified Incline Duct. And I'll tell you about that. He's now a professor at Rice. And as a result of the experiments that Colin did, we got a grant from the EPSRC collaboration between Colin Caulfield and Stuart DL and John Taylor, all in Cambridge, working with me, and Rich Kurzweil, who was in Bristol and now is in Cambridge. And that was a 5-year program grant. And then subsequently, we followed it up with STAMP, which is an ERC funded proposal. And the work I'm really going to talk about most recently was done by these 5 PDRAs, postdocs of mine, Sanyang Jiang, Gaopeng Kong, Amir Tufi, Adrian Lefauve, and Lu Zhu. So really the credit for what I'm going to say really comes from all their hard work, as you'll see as we go through the talk. Okay, so what is SID? Well, SID is a very simple experiment. You take a tank of water, you put a barrier in the middle, and you fill up one side on the left with dense fluid, and you fill up the other side on the right with less dense fluid. So you, for example, salty water on the left and fresh water on the right. And all we did was stick a pipe, in fact a rectangular duct, between the two sides of this barrier, and a hole in the middle. And we open the pipe and tilt it slightly from the horizontal. And that generates a flow. The dense fluid on the left flows downhill and it enters the reservoir on the right, and the fluid on the right, which is less dense, flows uphill and enters the other reservoir. This generates a flow in opposite directions, a shear flow with a density variation. And we can basically vary three parameters: the difference in density, the angle, and the properties of the fluid. So I'm going to talk about salt stratified flows and temperature stratified flows. So two properties of the fluid. That's all in water. What it actually looks like is this. So here is our tank. This is the barrier. Here's the duct. And we have two reservoirs. And we just set up, as I said, it's a very simple experiment. Okay, so let's first of all talk a little bit about the physics of the system. So we start off on the left with the dark, dense fluid on the left-hand side, the light, uncolored fluid on the right-hand side. We open the duct and the flow exchanges, and if there's no mixing in the system, of course, all the dense fluid ends up at the bottom on the right, and all the light fluid ends up at the top, and that everything ends. And if you plot that as a graph in terms of energy, it's a very simple system. You start off initially with all potential energy, because nothing's moving. You open the duct, the flow accelerates and generates kinetic energy, and for a long period, that kinetic energy remains roughly constant, and the potential energy decreases because of the exchange across the reservoirs. And finally, everything decays. The potential energy goes to zero, the kinetic energy goes to zero, and everything is in the internal energy of the system. So it's a very straightforward thing in global terms. And what we're interested in is this time, when the system is flowing and everything is at a kind of steady state. And the length of that time, of course, depends on how big the reservoirs are and things like that. So you can write the energetics in boxes. You start off with potential energy. That gets converted into kinetic energy of the flow. Some of that is dissipated, well, it's all dissipated viscously. Some of the potential energy is lost by mixing. And one of the questions we want to answer is, what is the ratio of those two dissipative mechanisms? And so what I'm going to do is to try and study the mixing in this simplified system. Okay. So I'm going to first of all talk a little bit about the sort of parameters in more mathematical terms. So essentially we have a shear flow, we have a density difference in the system, and gravity is tilted by this angle theta as we tilt the duct. And we write down the usual equations of motion, incompressibility, momentum, and conservation of mass. This is the diffusivity of the scalar field, in our case salinity or temperature. And if you non-dimensionalize this system, we get the following non-dimensional form. So we get a Reynolds number, which is based on the velocity difference, the depth of the duct, and the kinematic viscosity of the fluid. We have a Prandtl number or Schmidt number, which is the ratio of the molecular diffusivity or the viscosity to the molecular diffusivity of the scalar. And we have theta, the angle of tilt. These are three-dimensionless parameters. And we have a fourth dimensionless parameter, which is a Richardson number, which is essentially the buoyancy times the height divided by the velocity difference squared. Turns out in this system, as I'll explain, that number's fixed. So it's not really a parameter. So we have three-dimensionless parameters, properties of the fluid, and then the Reynolds number, which is essentially the density difference and the angle of tilt. So it's a very simple system with two controllable parameters if you fix the fluid. Okay, so let's see where we sit in relation to, say, a big, large-scale flow. So I've got on the right here the parameters. So the Reynolds number here in SID is somewhere, we work somewhere in the region of a few hundred to just under 10,000. Our Richardson number, as I said, is sort of fixed all around some number around less than 1. And the parameter number is the same as in nature, is either around 7 for temperature stratified water or 700 for salt stratified water. And theta we can vary as much as we like. And if we compare that, for example, with a river outflow, we're several orders of magnitude, of course, smaller in Reynolds number, although the Richardson number and the parameter number are comparable. And the example I showed you of the equatorial flow is even higher Reynolds number. So we're the biggest gap between what we're talking about in the lab and what happens in nature is really the Reynolds number of the system, and that's something that is very hard to overcome. I'm not going to talk about thermals, so we're talking about small angles. We're always very close to horizontal. We're not talking about convection. And we're not talking about all sorts of other things. So it's a simplified system. Okay. So this is the system. In a way, it's a trivial system overall. So I showed you the whole dynamics, but actually for the duct, it's quite complicated. It's complicated because we have these boundary conditions on the duct walls, on the side walls and top and bottom, no slip. We have no flux and density. And in particular, we have inflow-outflow conditions. So we bring in fresh fluid at one end, it mixes, it comes out mixed, and the same in the other direction. So this makes modelling it quite complicated, and you'll see how that works later. So we have non-periodic conditions in X, and a mean flow, which is a function of the span-wise and the vertical coordinates. Okay, so what did we discover? This I did with Colin, as I said, about 10 years ago. We first of all discovered that the flow is hydraulically controlled. How do we do that? What do we mean? Well, what we did was to open the duct, run the system for a while, stop it, measure the mass, measure the densities afterwards, and from the difference in density before and after, you can work out how much mass has been transferred. And if you plot that flux as a function of either the angle or the Reynolds number, you find that it increases, and then it reaches some limit. And that limit is associated with the fact that the velocity scales with the buoyancy times the height. Okay, so it's indicative of a hydraulic control. This is really important. It means that no matter what we do in terms of driving the system, we can't make the mean flow go faster than a certain amount. And you'll see that's really important for how the system behaves. And I would say that's serendipity. I didn't expect that when we set the experiment up, but it's brilliant because it makes everything else possible. We also discovered that there are 4 different flow regimes in the system. So depending on, and I'll show you what it depends on, we can find systems where the flow is essentially laminar and that you can't see any real disturbance, although the flow is happening. We saw a system where we see waves on the interface, and when we have salt stratification, these are sharp cusped waves known as Holmboe waves. We had systems where the flow was fully turbulent all the time, and other times when it was turbulent like now, and then would become quiescent for a while, like now, and then turbulent, right? But you see, right? So intermittent in time, and in fact intermittent in space. You can't tell from here, but intermittent in space. Right? So we find these 4 regimes, and if you plot them on a regime diagram, for example, you plot angle on horizontal and Reynolds number on the vertical. When you've got low Reynolds numbers and low angles, you're in this regime. As you tilt the duct a bit more, you get waves. Or if you increase the Reynolds number, you get waves. If you increase the Reynolds number or tilt the duct more, you get intermittent. And if you drive it as hard as you can, you get turbulent. And we thought we were absolutely brilliant. And then we should have read the literature because Enzo Macagno and Hunter Rouse in 1961 did this experiment and found these 4 regimes as well. So the lesson to all you students is read the literature. And it was my PhD student who found this paper. Yeah. Anyway, so how do you characterize these regimes? So we've taken the previous sort of schematic, plotting the actual data in log, Reynolds number theta. We find that those regimes, so laminar, waves, intermittent, turbulent, seem to scale on theta Reynolds number equals constant. These are the 2 parameters we have. And we want to try and explain why that's the case and how that works into the system. Okay, so that was the sort of looking at the overall structure, and then we then decided that the thing to do is to measure everything. And I think this is the step that really makes the difference with this particular piece of work. It's a result of the fact that we're now able to make very detailed measurements of flow that we couldn't do 10 or 15 years ago. We can measure the velocity everywhere, and we can measure the density everywhere at the same time in 3 dimensions. So this is what we do. We have our system, we shine a laser through the system, and we have dye in it, so that tells us what the density field is. And then we have 3 cameras. The 2 outside cameras look stereoscopically at a plane and measure the velocity in that plane. And the 3rd camera looks at the plane and measures the dye intensity, which tells us the density. And then we move the plane, essentially. So when you look at it from schematically, I said we have these 2 cameras that measure the velocity in this plane and perpendicular to this plane. This one measures the density in this plane, and then we move the plane back and forth across the volume to get the 3-dimensional flow fluid like that. And that gives us 3 components of velocity and the density in three dimensions, and enables us to really look at the turbulence and the mixing processes in this whole system. And so this is what you could see. So looking at a vertical plane, at the top is the density field. This is in a turbulent situation, so Reynolds number over 1,000, quite a big tilt at 6 degrees. 3 components of velocity, streamwise, spanwise, and vertical, and the spanwise vorticity, showing these long streaky structures which are very characteristic of this flow in turbulent systems. And we can also look at this in a horizontal plane. So we can do the same things in the horizontal plane. Again, the density field at the top, streamwise velocity, spanwise velocity, vertical velocity, and again the spanwise vorticity. So this gives us incredible information about these flows that we're able to then analyze and look at the properties. Okay. All right. So before I go into the details of that, I just want to say one other thing that exercises many of us in this whole area, certainly oceanographers. One of the questions is, how efficiently can you mix a fluid up? As I said, if you put a certain amount of energy into the system, for example, on the ocean, you're putting the wind energy in, how much of it is used to mix the system? The way to think about it is to have a bath, and after a while your bath gets cold, and you pour some more water in, and the warm water sits at the top. Okay, so that's up the top there. You're sitting in, and the red water is the water that you've just added and sits at the top. And you put your hand in, and you stir it around, and you make it uniform temperature everywhere. Okay. And what you do then is you raise the center of mass. So if you look at the center of mass, cm, for the first stratification, because all the buoyant stuff is at the top, when you mix it, the center of mass moves up. So you do work. And that works what you're doing. And the question is, how much of the work that you're doing is raising the center of mass, and how much of it is just being dissipated viscously? Right? So that if you think about the ocean and the wind, how much of the energy the wind is putting in is actually doing the mixing, and how much is just being viscously dissipated. And it's a complicated question, because you can imagine if you do this in your bath and you keep doing it when it's mixed, of course, you're doing more work and you're not getting any benefit. So it's a complicated question. But the question is, can you measure it and it's very important. Oceanographers think this number is 0.2, 20%. Okay. Everywhere in the ocean. It's unlikely. Okay, and we do it by measuring the viscous dissipation and how the density field evolves. And for those of you interested in this kind of stuff, you measure chi, the scalar dissipation, which is the diffusivity times the variance, square of the variance of the buoyancy field. And we can measure that, because we have all this data to measure. So that's one of the things we want to know. So as I said, this is what we're looking at, this transient steady state, and we want to measure this ratio. How much goes from this viscous dissipation? How much of it is mixing? What's the ratio in our experiment? Okay, so I'm going to talk a bit about the energetics and how these transitions take place. Okay, so we start off with the whole system as I've drawn, and then we just take the duct itself. The reservoirs are outside the duct, and then we force the system. We either increase the Reynolds number, or I think the easiest way to think about it is just tilt it a bit more. So we increase theta RE up the top there, and that goes initially into kinetic energy. That does some mixing, produces the buoyancy flux, and we also have viscous dissipation. And we tilt it a bit more, or increase the Reynolds number a bit more. So we do a bit more, and we get more viscous dissipation. We generate a bit of turbulence, maybe the waves at this point, a bit of buoyancy flux, a bit of mixing, and then we add some more kinetic energy, and this then produces even more flow. However, as I said, the flow is hydraulically controlled, so the mean flow can't go any faster. So this bit, that goes from mean to viscous dissipation, just becomes limited. And so what you get now, as you put more energy in, is you produce turbulence, as you saw. You got to a more turbulent state, and that turbulence then dissipates. It also drives the buoyancy flux, which produces mixing. And we're now able to measure both those quantities from the three-dimensional velocity fields, the density field that I showed you. So we are able to measure these things in parameter terms, the psi, the viscous dissipation for turbulence, but the mixing from mixing. Oops, sorry. So we are able to measure this mixing efficiency, and also what's called the flux resistant number, which is the buoyancy flux over the production. From our experiments, we get numbers which are actually smaller than 0.2. We get 0.1, and we get values for the flux resistant number, which are 0.05. I mean, that's, in a sense, that's just to say that we're able to do this. And this is for this particular flow. It doesn't mean it applies everywhere, but it's the first time I think you can measure it in those terms.
Which regime are you in that for?
Okay, sorry, yes, not very clear, is it? So T1, T2, and T3 are the three most turbulent cases, and I are the more energetic intermittent cases. Okay? So, yeah, so the waves in the Laminar cases are not clear. Yeah, good question. Yeah. Sorry, I'm so familiar with the color code, but yeah. Okay. All right. And just to say one other feature that you can deduce from these experiments. So as I said before, the transition, from laminar to waves to intermittent to turbulent, go on this theta Reynolds number constant terms, and we can look what happens if we stay on one of these regimes on a line of constant theta Reynolds numbers. So let's suppose in the turbulent case, for example. So here is the line of the turbulent case at constant theta RE on the theta RE log plot. And then we measure the entropy, so how much of the fluid has high levels of vorticity. So this is indicative of regions which are being strongly strained. And when we do that, we're able to see that scales in the same way. So it scales like theta Reynolds number Q, but it's parallel. Okay. And we can also look at the fraction of fluid that's overturned. So how much of it has dense fluid on top of light fluid as the turbulence evolves. And in that case, we find that it's a different power law. So as we move down this curve on the same regime for the same turbulent flow, as we go from high angles, we find that we have more overturning, because we are over here, compared to entropy. But when we come down to low angles and high Reynolds number, we have more straining and less overturning. So you can see, even for the same flow regime, where it's fully turbulent on the same theta r, you get different forms of the structure. And we've looked quite a lot at the structure. I may have time to say a little bit about that there again. So that's one of the fascinating features of this system. Okay. So I want to tack a little bit now and talk about DNS and what you can do with DNS in the system. Right, so this is the experiment, and we're now building a really brand new experiment shown here. So this is the new system. We have much bigger reservoirs. We have a fancy duct, and everything is lifted by an electronic motor, and it's a huge. I mean, normally I do experiments that fit on a tank like this, and I said to my students, when you double the size of anything in a lab, it goes up like the cube, right? Because it's the volume. So what took you an hour will now take you a day, right? 2 hours takes you a day. Okay. And they said, yeah, you're right, it takes forever to build this. And anyway, we've got this new fancy thing, and what we do with the experiments, we're able to do things like high Reynolds numbers. We have real fluid, real boundary conditions. Diagnostics we can do, but it's difficult. Quite hard to do those measurements. And our resolution is moderate. You know, so we can get down to the Holmboe scale for moderate Reynolds numbers. That's good. We can't get down to the Bachelor scale, for those of you who know about those things, where molecular diffusion matters. But we can do long experiments. Okay. If you look at DNS, it's quite difficult to run things at high Reynolds numbers, actually. And usually, DNS simulations use idealized boundary conditions. They use periodic boundaries. And I told you this has got no periodicity at all. Diagnostics are very good. They can measure everything. And resolution is very good. Usually down to Commodore scale and in many circumstances. Quite hard to do long time resolution just because of storage issues. So there are pros and cons, but we thought DNS is worth simulating. So I'm going to talk about that and what you can learn from that. So, same equations, and we run DNS simulations of the same systems. Okay. So this uses a solver called XCompact 3D, and it uses an inverse boundary method and it represents the boundaries of the duct exactly. So these are no-slip boundaries with no fluxes, and we then have reservoirs where we artificially reduce the velocities to zero and restore the density to the original value. And we do that in the momentum and mass equations by these two forcing terms that are in red, which essentially slow the flow down here, restore the density, and allow it to carry on as before. So, and when we use thermal stratification, which I'll show you some experiments where we have done that, we match the Prandtl number, which is 7, exactly. So I think this is the first time in my career that I've ever had a DNS that has exactly the same conditions as an experiment that I've done. And it's fascinating. And it's down to Luzu and Amir Atufi who do this stuff. And as you can see, here's the density field and velocity field for one of these intermittent cases. So, that's how well does it work? Well, you can see all 4 regimes. So the laminar regime, you can see wave-like systems, an intermittent case, and you can measure you can see a fully turbulent case. So we get the 4 regimes that I showed before, and if we plot them on the same Reynolds number theta phase diagram, we see that they overlap with the experimental ones. So these are experiments done with temperature, so the same molecular properties as the DNS. The big symbols are the computations and the little symbols are experiments, and you can see that the same colors which correspond to the same regimes match. So that's, I think, really fantastic. So we think we're able to simulate what we see in the lab exactly. So what's the advantage of doing that? Well, as I said, there are various things about diagnostics. But before I do that, let's just show you again how good these comparisons are. So the top panel on the right is the experiment, and it's a shadow graph, which means you shine light through the system and look at the image on the screen. And the bottom panel is the DNS representation of the shadow graph. And I hope you'll agree that this looks pretty similar for the wave case, and quite different from the salt ones I showed you, because the interface was quite different, and with little sharp crested waves, we don't see those at this lower craft level. And we can look at the intermittent case, and again you can see, I think, really remarkable agreement between experiments and DNS. And even looking at properties such as time variation. So this is the space-time representation of, in the intermittent case, the DNS and experiment at different angle, and again, same structure, same time variation. So we're pretty confident that these DNS represent what we see in the lab very well. So what can you learn that you couldn't learn from the experiments? Well, a couple of things. One is, of course, you can see the whole duct in the experiment. Couldn't do that in the lab because our cameras won't let us do that. So you can see the structures along. So we found that it is intermittent not only in time up here, but also intermittent in space. So periods where the flow is intermittent, both spatially and temporally. And we can look at time series along the whole duct of the kinetic energy, for example. But more interesting, I think, is we can look at what happens to controlling the system. So one of the things I said when we did our very early experiments is that the flux through the system, the amount of exchange, is limited by this hydraulic control, that the system can't go faster on average than a certain limit. And these are more experimental data, and it shows that the flow accelerates or increases as you increase the Reynolds number until you get to this value of a half, and then it sort of never goes any faster than that. And we find the same in the numerics. The flow starts off slow, and then as you increase the forcing, it reaches a half and it stays close to a half. So the flow is controlled in both cases. But we can look at how that works. And I think that's interesting. So, and the way you can do that is look at the pressure. Okay, so at the top is the Laminar case, and the colors correspond to the pressure, and the lines correspond to the density field. Okay, so let's look at the top picture first of all, and look at the lower layer, which starts red on the bottom on the left, and goes all the way through to blue on the right. So the pressure is high on the left, and becomes low all the way down the lower layer on the bottom. So the pressure gradient is pushing to the right in the lower layer all the way along. And if you look at the upper layer, the pressure is higher on the right, and it becomes low on the left. So the pressure gradient is to the left in the upper half, pushing that layer the other way. That's what you expect. You get this exchange flow. On the other hand, if you go to the wave case, you see that's no longer true. So the pressure is high here, gets low there, but then it gets high again. Okay? So the pressure gradient here is prograde, it pushes the way you want to go, but when it gets to here, it starts to decelerate the flow. It's retrograde. Okay? So now, the system is behaving quite differently. Okay? So whereas the hydraulic control in the Laminar case is associated with the flow over the end of the reservoir, because that's what you normally expect to flow over a weir, is your hydraulic control. Here, the hydraulic control is caused by the pressure minimum in the middle of the duct. So what you're actually doing is trying to push fluid down this duct too fast from both directions, and it goes, oh, in the middle I can't cope with this. So it goes for an internal hydraulic dump in the middle, and everything slows down as it exits the other end. And it's even more pronounced in the intermittent case, where the minimum is larger and extends more. And you can see that when it does go turbulent, things change again. So it's quite different dynamics, and we can't see that in the experiments. They can't measure pressure, not with that resolution. So this is very interesting insights. And you can look, for example, at just how, if you look, for example, at the upper layer velocity or the layer heights, you see regions where you get transition in the middle of the ducts in the wave cases, these two wave cases, and the intermittent case. Whereas in the laminar case, the changes take place at the excuse me. Okay. All right. So just to come back to one final thing about the stratified shear flow in a more general sense. So one of the things that I want to sort of come back to then is how you look at it from a large overall perspective. So the classical case, let's imagine this very classical case of a uniform gradient of density. So the buoyancy increases from the bottom B to B plus delta B at the top, where the buoyancy is defined here in terms of gravity and the density difference. And the shear goes from U to U plus delta U and uniform. Okay? And from that you can construct a parameter called the Richardson number, which is the depth of the duct times delta B times delta U squared, and that's a dimensionless quantity. Okay? It just tells you the overall stability of the system. And you can think about it in energetic terms. So if I have a little blob at the bottom and I make it go up to the top, the change in potential energy of that is H delta B, and the change in kinetic energy it experiences is delta U squared. So for that to happen, I have to have this number, I have to have more kinetic energy than potential energy to do the work. So this number has to be less than 1. Okay? If you go to the ocean, for example, and take the depth of the ocean of a kilometre, typical speed difference from the top to bottom, and different buoyancies, you find the numbers big, 10. So how does it happen? How do we, because we know it mixes, so how does it happen? And I want to go full circle back to my supervisor, and if you haven't read this book, you should read this book. He said, well, the way to solve the problem is you don't have uniform gradients of density and velocity everywhere. You break it up. You have regions where the density gradients are small, and then you have regions where the density gradients are large and the velocity gradients are large. And then you define your Richardson number in terms of local gradients. And because this is a square, you can always make this as small as you like. And so he said that's what should happen. So it doesn't happen in our experiment, and if so, how does that organise it? Okay, so this is what, as I said, what we find. And what we find is we have this central mixing region in the turbulent system. So we end up with 2 of these little interfaces with turbulence on either side. And in the schematic, it looks like this. We end up with these gradient region, Richardson number regions in these interfaces. And you can just do the sum. So the gradient Richardson number is just based on the local density change and the local gradients. And in this particular experiment, as I said, because of hydraulic control, this quantity is always a quarter. So what we find for what we expect on these interfaces is that the gradient Richardson number is the thickness of the interface divided by twice the total depth of the system. So we can measure it in the lab. So we measure the gradient Richardson number. These are for all the cases, but let's look at these 3 turbulent cases. We find that the gradient Richardson number is always somewhere around 0.1, 0.2. you can actually plot a histogram of it, and you find that the really turbulent cases, the ones that are in red, have this gradient resistance number at these edges of about 0.1 to 0.2. And if we look at the structure of the system, and we find that there are these interfaces at top and bottom of the mixing region, and this ratio, delta over H, is about 0.3. And so, as I said, it should be about delta over 2H, which is about 0.15. So what we're seeing in our system is this breakup of the uniform gradient into these layers and interfaces, which characterize themselves with a gradient resistance number of about 0.15. The question is, why is that the number? I don't know the answer to that question. So, something else to think about. Okay, so that basically brings me to the end. As I said, we had a bunch of questions. What form does mixing take place in stratified shear flow? And I think I've showed you that it depends on on the energy of the flow. It also depends on some of the details of the geometry of the system. Can we predict the mixing rates from mean velocity and density fields? And I said, in our case, the mixing efficiency is about 10%. How do they depend on the fluid properties? It's a different temperature and salinity, and I think I showed you that the structures are actually different. And I think it's a very interesting question. If you take the ocean, stratified with temperature and salinity, what is the right diffusivity? Is it the temperature diffusivity? Is it salt diffusivity? Different by a factor of 100? Or is it something in between? We don't know. Okay. And what are the energetic pathways? Well, we see production of turbulent kinetic energy leading to irreversible mixing through straining and overturns. And with that, I'd like to stop. Thank you for your attention.